Good morning, good afternoon, good evening, wherever you're situated. Um, it's a pleasure to be here once again. Thank you for the opportunity, Ibrahim. Today I'm going to be talking about cloud computing and high performance computing for biomedical research, particularly because sometimes we talk about cloud computing, but people don't know why they need cloud computing. So we talk about data centers, we talk about GPUs, we talk about all sorts of things. But for some people, it just sounds like jargon. Like, what are these people talking about? Um, why can't we go out and buy our own computers and do what we need to do? All right. So in this session, we're going to look at biomedical research and why uh, you need data centers and high performance computing. So, why this topic matters? First of all, it's because research requires massive amounts of data, and that data needs to be processed. So, if you look at the core of modern biomedical research, it relies on data analysis to uncover patterns, correlations, and insights. So it's not just about collecting data, but it's about processing the data that you collect and store. Uh, Nowadays, we don't call it big data, but there was a time we used to call it big data. And big data has certain characteristics. We have volume, which is the size of the data. What that means is you have to think about different types of data like medical imaging and think about the actual storage size on disk. We also talk about velocity, which is how quickly data is being generated and collected. There's also variety, which is the different types of data that is being generated and collected. Okay. And we got to a point where these three things started to outpace the traditional computational capabilities that we're used to. So if you're used to computers, you might think, oh, okay, we're in a medical facility, maybe a hospital, maybe a research facility. We can go out and buy computers. We can go online. We can go to the Dell website and we can buy computers. Okay. Another reason why this matters is that you have different fields. So again, we go back to how we're generating data, the rate at which we're generating data. But when you start to think about things like genomics or medical imaging or epidemiology, then all of these things translate to exploding data volumes. All of these fields are generating vast amounts of data. Now, right back to the traditional infrastructure, why can't you go to the Dell website or the HP website and buy a server? It's because that approach can be costly, but it can also be slow. So you might think, yeah, I can go online and buy a computer, but what sort of computer are you buying? How many processors does the computer have? How much RAM does it have? How much storage space does it have? And then the more important question, how quickly are you going to fill up that storage space? Okay. Um, Now, when we come to cloud and high performance computing, they have certain benefits. It helps us to unlock speed, scale, and cost efficiency. And we're going to talk about these very shortly. So let's look at a very high level definition for these two concepts, cloud computing and high performance computing. Cloud computing generally refers to someone else's computer. So not your computer, but someone else's computer. But we're not talking the computers of individuals. We're talking the computers of mega corporations. So think Google, think Amazon, think Microsoft. Now, these computers are made available on demand. What that means is you get these resources when you need them and you free them up when you don't need them. In general, you get them when you need them. There are times when there's high demand and you might need to wait a while to get these computers, but on the average, you get them when you need them. Now, you also get what you need. So think of it as slices. You get a slice of what you need. So it's scalable. And you specify what you need. How many processors do you need? What type of processor do you need? How much storage do you need? All of those you specify. And that's because the owners of the infrastructure have designed it such that there's a transparent layer between, would I call it transparent layer? But there's a layer that kind of it fuses everything together. So it doesn't matter the specific number that they have. What you're really thinking of is what you need. Now, because it's on demand, you also have a pay as you go model. And I think the world is now used to pay as you go models. So you simply just pay for what you use. So what that means is if you need a computer for 3 hours, you pay for the 3 hours. You don't need to specify at the beginning that you need it for only 3 hours. So that way you're not under pressure. You use it. When you're done using it, you shut down, you free up resources, and you get billed for just the time that you used. And then we have one benefit, which is global accessibility. What that means is wherever you are, you can access cloud computing resources. Uh, so even if you could set up the same infrastructure locally, you would have to worry about global accessibility. There are, of course, other things you have to worry about: powering the servers, cooling the servers, access to the internet for the servers, and things like that. So that's cloud computing. It's someone else's computer that you get to access when you need it. Now, what's high performance computing? You would think of it as parallel computing using clusters of powerful machines. So where do you get these machines? But then how do you set up parallel computing? So again, you could go out and buy a few servers, but do you have the expertise to set up parallel computing? And this isn't just, software knowledge, like networking and stuff, but you also have to think about the fabric that connects these things together. You have to think about um, the job scheduler that takes the job, slices it up, passes it out, gets the results, aggregates them, and presents them to you. So high performance computing gives you parallel computing capabilities. As a result, it helps you solve extremely complex or large problems quickly. And so what that means is there are certain computational tasks that will not fit into the memory of a single computer. Um, and even if it does fit into the memory of a single computer, the limited number of processors on that computer means that you're going to spend a really long amount of time just waiting for the task to get completed. But when you have parallel computing in place, it means that that task will get split up into chunks and passed out to different processors that will compute various components of that task and then return their results. So high performance computing is ideal for simulations, modeling, um, analysis of massive data sets. Okay, so why do we need both? We need both we need both cloud computing and high performance computing for certain types of tasks that are common in biomedical research. So think genomic sequencing, think large scale imaging, disease modeling, drug discovery simulations, population level analytics. So electronic health records, epidemiology, things like that. Cloud computing and HPC put together deliver value. So what are some cloud benefits for researchers? The first one is elastic scaling. When we talk about scaling, what we're saying is you don't pay for what you are not using. When we think about research and grants, you hear about people getting grants to do research, and you start wondering, okay, are you going to go buy servers and just come keep? It's not a good use of money, right? But if you have access to elastic compute, what that means is you can plan out your your jobs, and then you can request the kind of compute that you need. If you need 64 processors, you ask for 64 processors. If you need 6,000 processors, you ask for 6,000 processors, right? Now with cloud, you're able to do a few interesting things. You can start jobs on, a few machines, and then you can request additional machines to speed up the job. Standard machines have a standard rate, but cloud providers typically have what they call preemptible virtual machines. And what that means is, I don't need this right now, so I can give it to you at a fraction of the standard cost with the condition that I can yank it when I need it. Now, the benefit of such an arrangement is that you could save up to 75% of the cost, and the compute, the servers will be made available to you, and they'll do the tasks that they need to do. They could be yanked off, and when they get yanked off, what that simply means is that it just takes longer for the remaining computers to complete the task. But there's a cost benefit analysis. But there's a benefit to the cost when you look at such an arrangement. Cloud gives you massive storage capability. So usually we're talking petabyte scale. A petabyte is 1,000 terabytes. So if you had to go out and buy one drive, or you had to set up a petabyte of storage, you can imagine how much it costs. But usually, in these sorts of fields, you want to have redundancy, so you don't buy one. So you don't set up, if you want to store like a petabyte of data, you don't buy 1 petabyte of storage because you could have failure. So you have redundancy in place. And so what that means is if you need a petabyte, you might be buying 4 petabytes, you might be buying 5 petabytes. That's if you had to do it yourself. But with cloud, you get that redundancy built in. And all you have to do is just, keep collecting your data. If it's imaging data, keep collecting your imaging data. And then, you just request. In fact, you really don't get limited in terms of storage. You just get billed at the end of the month. One benefit of cloud is that you get collaboration across institutions. So if you have researchers in multiple geographical locations, they get access to the same cloud. If you had to set up your own infrastructure locally, you'd have to worry about all of this. You'd have to worry about some sort of high quality internet access that gives people connectivity. But what that also means is that, on the one hand, you need connectivity in all the geographical locations to access your infrastructure. But your infrastructure also needs a fat pipe to send data out. Usually, pipes are optimized for downloads, but not for uploads. Again, the pay as you go uh, pricing model is one key advantage for cloud. You do get things like committed use discounts. So if you're certain that you're going to use something for a certain period of time, you can opt in for committed use discounts, and that gives you even greater savings. A lot of the cloud providers have integrated artificial intelligence and machine learning tooling within their infrastructure. And that saves you, again, the headache of having to set that up locally. When we get to high performance computing, some of the advantages are speed. So you can significantly reduce computational time compared to traditional desktop or even traditional cloud computing. So in this case, we're layering high performance computing on top of cloud. You do have the benefits of scalability as well. So you can scale computational resources, and you can do that either way, scale up or scale down to meet your workload demands. You have the benefit of parallelism. So you can leverage multiple processors or cores for massive parallel processing, which is crucial for complex calculations. You have things like resource management, data handling. So when you look at certain things like high resolution molecular simulations, what you need to do here is simulate the behavior of molecules, proteins, DNA, etc. at an atomic level. This involves calculating forces between atoms to understand molecular dynamics and interactions. So when you use high performance computing, you get the computational power that you need because these computations are numerically intensive. You can get GPUs that are clustered, which again speeds up your processing. Uh, Same thing with memory. So sometimes these computations will not fit into standard memory, but they can be broken up. So things like high resolution simulations require significant memory. When you look at something like protein folding and binding prediction, you have 3D structures of a protein from its acid sequence. You need to predict that. You need to predict how a molecule, e.g., a drug, binds to a protein target. Computing these is again computationally intensive. We have things like cryo-electron microscopy data processing. In this case, you have the electron microscopes taking lots and lots of images that you then need to put together. Processing images is computationally intensive, right? And we can keep going down the stack to look at what sort of processing requirements we have in place, given the types of tasks that we need to carry out. But the point here is when you stack high performance computing on top of cloud computing, then you get the necessary resources that you need for your jobs to get done. So, what are some of these cloud platforms? Google has one, Amazon has one, Microsoft Azure has one, and then you have some specialized platforms out there. And each of these platforms, they all have their strengths, they all have certain resources that they provide. So Google Cloud Platform has, for example, BigQuery. BigQuery is a petabyte scale data analytics warehouse. So it lets you store data, uh, query the data, perform analytics on the data, even perform some level of machine learning inference on the data so you can train models with the data that you have. Google Cloud also has something called Vertex AI, and think of Vertex AI as their artificial intelligence platform. You get all sorts of resources for storing your data, training AI models, carrying out inference on those models. You also have the cloud healthcare and life services APIs. The difference between APIs and things like AI platforms is that APIs are pre-trained for certain tasks, and all you have to do is programmatically call these APIs, pass your data in, and you'll get responses. They also have something that they call TPUs. So these are slightly different from GPUs, but they carry out the same functions. So TPUs are tensor processing units, and they are called application-specific integrated circuits that are used for speeding up numerical computations, particularly where you have some sort of floating point arithmetic that you need to do in a vectorized manner. The other cloud providers have uh, something similar, not exactly apples for apples, but depending on your cloud provider of choice, you can always go take a look at what it is that they have, take a look at the infrastructure descriptions, and then read the docs to see what it is that you can do and how to get started. Let's look at some examples of real world biomedical workloads. So we have things like genome variant calling pipelines, and what you do here is analyzing raw DNA sequencing data to identify variations in the genome. Examples of these are single nucleotide polymorphisms, insertions and deletions in DNA sequences. And this is a cornerstone of genomics research. The outcome of this is understanding things like disease susceptibility or personalizing medicine based on a person's genetics, and even things like evolutionary biology. The challenge here, or some of the challenges, are things like massive data volumes. And that's just because sequencing generates enormous data sets. Every sample tends to generate terabytes of data. Okay, so storage needs to be efficient. When you look at cloud providers, they tend to have a really fat and wide connection between storage and processing. This is something that we typically don't think about with standard computers. Even when you go out and buy servers, your compute might be separate from your storage. And then how do you quickly move data between storage and processing? That's usually a very interesting problem. But the cloud vendors usually solve for these types of problems. We also have things like cryo-EM reconstruction. And here, what you have to worry about is reconstructing 3D structures of biomolecules from cryo-EM images. And this usually involves processing thousands of 2D images to generate a 3D map with atomic level resolution. So again, dealing with images, first you have to store the images, second you have to process the images, and you have to process them quickly. Where you don't have a proper bandwidth between storage and processing, you tend to have bottlenecks, and those bottlenecks show up pretty quickly. Again, there are various examples going down the list. I'll just skip them, and I'll go to the next topic, which is talking about data management and compliance. So when you don't store your data locally, that's when you don't have your servers local, but you have them in the cloud. What are some of the data management and compliance things that we need to worry about? In the US, they have the HIPAA. In Europe and around the world, we have like GDPR. It's called various things, but there are regulatory requirements. The cloud providers, depending on the kind of service, so we tend to have things like infrastructure as a service, software as a service. Uh, they worry about certain of these regulatory requirements. And then, depending on how much involvement you have, you also have to worry about your own regulatory requirements. There are things like secure access controls. Of course, for the cloud providers, they have physical access controls in place, but they give you remote access, but you also need to manage your own remote access. You need to ensure that you're not sharing credentials. Multiple individuals are sharing credentials, so that way you can audit who's accessing what. You can ensure that people aren't using weak passwords. You can ensure that you have second level authentication in place. So what that means is a username and a password are usually not enough. You have something else, a second factor. Sometimes in some organizations, they use a hardware security key to secure access. So sometimes you might see people with laptops that require the insertion of a smart card or a Bluetooth token that needs to be close to the laptop when people are working. Nowadays, some phones are used as a second factor, or we're even migrating away from passwords, but all sorts of implementations in place. Encryption. So we have two levels of encryption: data at rest and data in transit. Data at rest sometimes is guaranteed by the cloud provider. Sometimes you have to set it up yourself. Usually for data at rest, you have security certificates. Again, you can use provider managed certificates, or you can provide your own certificates, worry about your own key rotation, set your schedule, and things like that. Data lifecycle management. So, what needs to be stored and immediately accessible? What needs to, so we could call that hot storage, what needs to go into cold storage? What needs to be stored for a period of time in the event of some legal request for access to that data, what can be deleted after a period of time, audits, logs, and governance around those. So do you track everything that people are doing? Do you have visibility? If there's a breach, do you know how that happened? Are you able to lock down the breached credentials immediately? Do you have controlled research environments? So what that means is how does a researcher access your projects in the cloud? Do you have things like virtual private clouds? Do you have, depending on the scale that you're in, things like cloud interconnect or a provider level interconnect where some internet provider has to set up a secure tunnel between your premise and the cloud because of the nature of the data that you're dealing with. So these are some key considerations to bear in mind under data management and compliance when you deal with cloud computing. And what are some challenges and risks? The very first one on top is high cost without optimization. Mistakes happen. Bad scripts can trigger heavy workloads, something that, a task that should have completed in 24 hours could end up taking an entire month to complete. And then if you have things like horizontal scaling in place, you could just start launching virtual machines to process badly written code. And what you then end up with is bills at the end of the day. So it's always important to optimize your workloads. Now, as much as we say that it's easier to work in the cloud, and it's true, you still need skilled professionals. So you need individuals who have experience with deploying these sorts of workloads. Of course, you can send your own engineers for training, or you can hire individuals who are already trained and experienced in these things. But trying to go it yourself is not always the best idea. Yes, we do have ChatGPT that can answer all sorts of questions. But the problem is if you ask ChatGPT to generate certain types of scripts and you don't even have the experience to review the scripts and ensure that uh, they don't have errors in them, then you're still going to end up with bills. So it's always important to not be penny wise and pound foolish. I've mentioned data transfer bottlenecks. These are things to worry about. And how this works is if your data isn't in the right format or isn't stored in the right location, and examples of locations are, you don't want to have your data storage in California and your processing in the UK. There's quite a distance between that. Even though you have good bandwidth, you typically want to have your data and your compute in the same data center, and that tends to eliminate bottlenecks. There are vulnerabilities. Vulnerabilities come up sometimes in the software packages you're dealing with, sometimes in the operating systems you're dealing with, but they come up. So it's always important to keep an eye on these vulnerabilities. There are security advisories that you can read. So if you're working with any sort of software, you want to keep an eye on that. Even databases, if you use a self-managed database, then you have to be aware of the security vulnerabilities that come up. And then finally, poorly designed pipelines, which ties back to point number one and point number two. So these are things to keep in mind. Going cloud plus HPC, is it a silver bullet? You need to be aware of what could go wrong and mitigate that. And then it helps to talk about future trends. So areas of ongoing research or things that could become reality very soon. So things like exascale computing for life sciences, future trends, because data is getting really massive, and so we're getting to the point where we need much better infrastructure, processors, GPUs, those sorts of things. AI accelerated high performance computing. And so, we have hardware, there's what we can do with hardware, but then now we're seeing certain AI models coming to help with breaking up tasks and scheduling them and then recombining the results. There's also federated learning for things like cross-hospital collaboration. Federated learning is a method of improving machine learning models without retraining the primary model, but instead using local data. And so in this case, not transmitting the data anywhere, but using local data to fractionally improve a model locally, and then taking the weights of that model and sending them back up, and then those get recombined, and then the central model is now improved and then sent back down out. So think about it this way. If you have an Android device, the fact that you can wake up your Android device using voice and then talk to it, give it tasks to do, is because you have a model, a local model on that Android device. Now, that model can get improved by your voice, by the kinds of instructions that you give, without transmitting recordings of your voice or your instructions back to a central server. Instead, your model will get improved locally, and then your model can send back its weights, and its weights are usually just floating point numbers. So it doesn't carry any information that is specific to you. But those can now get sent back upwards, and then the next model that will be deployed to your device is improved by all of these micro improvements from all the billion or so Android devices that we have in the wild. Okay, so that's federated learning. And then we're also seeing quantum computing come into the mix as well, an area of active research. And then we have new cloud native biomedical research platforms that are coming up. Okay, so that's it. I've come to the end, and I have a summary screen that just talks about how data intensive the field of biomedical research is and how cloud computing and high performance computing can help accelerate discovery and reduce costs. And that's it. That's the end of my presentation. I'm happy to take questions.